Um, I'll be talking about propagator networks and how we could apply them for degenerate computation. So, what is degeneracy? Degeneracy is when you have multiple implementations of the same function. Like this is very common in biology. For example, we have two lungs, two kidneys. We have we have more capacity than we strictly need to perform some function. But somehow in computing at least we are stuck with a very scarcity mindset from the 70s, from the history of computing, because we've always never had enough memory or enough CPU power to do whatever we wanted to do. So we've always been trying to optimize for performance above all else, above things like readability or maintainability and easily modifying programs and so on. And even though now that we have a lot more computing capacity, we are still stuck with this mindset, and that's something we need to challenge and fix. Obviously, there are things there where performance is still critical, and you cannot always sacrifice performance. But there are a great deal of things where it's not important, and we still write such things in languages like C, for example. So this talk is about propagator networks. It's really a general purpose system of plumbing for software. But my goal is to mainly talk about it for degeneracy. But I will first introduce what they are and the general idea before going into the degeneracy aspect. So yeah, so most of this talk is really based on the Software Design for Flexibility book. There's a chapter on propagator networks, and you should definitely check it out. Yeah. So propagator networks, what are they? It's a network of cells and propagators. So in this picture, the red circles are the cells, and the green boxes are the propagators. The cells are like the places where you store information, kind of like a variable in traditional programming. And propagators are pure stateless functions that take input from the cells, compute something, and write their output to an output cell. So any time the input of a propagator changes, that propagator is run, and its output is computed and put into its output cell. Like that is all there is to a propagator network. But the consequences of this are pretty wide-reaching and very interesting. So let me start with a really simple example. This is a tiny propagator network to square a number. You have one input cell x, and that's a squaring propagator, and its output is written to an x square output cell. So initially both the cells could be empty. Then we put let's say the number 2 into the input cell. It gets squared, and number 4, the result gets written into the output cell. So it doesn't end there though. We could also have something less directional. So in most programming languages, we are really stuck with expression orientedness. So any program, no matter how large, is really a large expression tree where you are bubbling up values from the leaves all the way to the top and computing something. Propagator networks allow us to escape this directionality. So here we have, there is really no way to express the equation y equal to x square in a expression-oriented languages. All you can do is express an assignment that x square is assigned to y, or the square root of y is assigned to x. Whereas with the propagator network like this, we can actually express the constraint, the equation, rather than an assignment. So again, example, you could have both cells initially empty. You put in 2, we get 4, just like last time. But we could equally go in the opposite direction. That is, let's say we have both cells empty. We put in 4 here, and then you get 2 there, right? So yeah, we have in a sense escaped the directionality of the expression-oriented languages. Now this is again a very trivial example, but I'll show a more complicated example later. And usually we abbreviate something like this with just a single undirectional propagator. So you see the trapezoids here, and this is just a box, which is a constraint rather than a directional propagator. The C colon is indicates a constraint. So likewise, this is a sum constraint. You really want to express z equal to x plus y instead of assigning specific, instead of these three different assignments. So you can see that there are three different functions here. This is the z equal to x plus y1. This is the x equal to z minus y1, and this is y equal to z minus x. Once again, we can abbreviate it like this, so that we don't have to think about the more complex direction one all the time. So, so the examples I've shown you so far are really trivial, but you can imagine something much more complex like this. It is built up of simple propagators like multiplication, addition, and so on. But it is a much larger network with a lot more variables. And once we express something like this, we don't have to think about what cells are the inputs and what cells are the outputs. You can compute the unknowns from all the other knowns. And this is not something that you can easily do in a regular expression-oriented language. You always have to build in some direction into the whole thing. So think about problems like type inference. Type inference systems are pretty hard to implement in a regular language because you want to somehow escape direction and put together a lot of partial information. That's a lot easier to express as a propagator network than in a regular language. So I said earlier that cells actually accumulate partial information, and it's not that the cells. It's not that. So when you have two propagators like this, the output does not get overwritten into the cell, but rather merged in some way. So you have to define some merging function. So in this case, there are each one of these propagators are outputting partial lists. So the underscore signifies an empty place in the list. So the first list has 1, 2, 3, 4, 5, but without the 2, and this one has 1 to 5, but without the 4, and these get merged into 1, 2, 3, 4, 5. So you can actually piece together partial bits of information in some with some way, and that could help you build up a larger result. And this merging of information is quite critical to many of the propagator networks properties. Like with type inference, again, you have lots of little pieces of information, hints from the code and from maybe type hinting, and you want to merge that into as complete a picture as possible. Okay, I do have 3 examples. I'll actually show you some code. So this is a degenerate network. So here you have the input x, and the output is x raised to n. Here we are actually computing this exponentiation in using 2 different propagators. So exponent function is the built-in scheme function to raise something to an exponent, and the other way is maybe you could write a loop which will multiply 10 times. So the idea here is that you have both the implementations in the final result, and when you merge it into the output cell, if it doesn't match, it's not mergeable, and you can raise a contradiction and do something about it. Or maybe you can prioritize one propagator over the other, and thus you could maybe report a bug to the developer or something like that. So this is degeneracy. Yeah, maybe you're writing maybe you want to rewrite your software in scheme, but Is the font big enough? Let me make it bigger. I don't know. Yeah? It's okay. Yeah. So you have two cells here, x and y, and one is the square of the other. I put in 2 into x into the cell called x, and you see the value at the bottom. You get 2 and 4, but I can do the other way as well. So let's say I do 4 here. I put 4 into y, and you still get the two results, the x and x square. So maybe I can do something like 5. Should get 2.26. Yeah, 236. Yeah. That's the squaring thing. This one is this is exponential. Let's leave that. And this is the one with the Bessel functions, right? And finally, the Gemma one. So, so the Gemma one I actually call Gemma in one propagator, and I have a scheme implementation in the other. Let's evaluate it. It will take a bit of time. And finally, we should get a big kinship matrix from the REPL. Yeah, any moment now. I hope I didn't trash the REPL or something. Oh, there you are. Yes. Yeah, you saw the kinship matrix, right? So, getting back to the presentation. And finally, to summarize, cells only merge or accumulate information. This is like a really critical idea that makes propagator networks work, and it's really responsible for all the properties. And then you can do things like track provenance. That is, you want to, once again. So you want to be able to track which particular path of the network was responsible for the result that you got. So if there is a bug, if there is a mistake, you can track it down and isolate it to a specific part. It's highly parallelizable, of course, because these are all pure stateless functions. It's trivially parallelizable, and you can also run this on the propagators need not even be on the same machine. They could run on a different machine. You could send it over TCP or something, whatever. And partial results are actually actionable. I didn't quite explain that in the rest of the presentation. So if you have an iterative algorithm that produces some approximate estimate, some early very crude estimate of a result, you can actually start acting on it in the later blocks without having to wait for the most refined result. So if latency in your workflow is important, it's critical, you can actually act on partial results like that. Then of course free from the directionality of expression-oriented languages, and then this is really useful for things like logic puzzles and I don't know, logic inference, type inference, things like that. So that's it. Thank you.
This is super cool. Thank you. This looks a lot like constraint logic programming also, or relational programming. It's very similar. Have people tried compiling these propagator networks to hardware, to like FPGAs or things like that? Because it looks like, these are basically circuits, or they're very similar to circuits. It seems like you should be able to compile them into hardware.
Right.
Do you know if people have tried that?
I haven't looked at what people have done yet, but it does seem very, it is a circuit, you're right, but I haven't really looked at what other people have done.
Okay. And do you have a type inferencer written
not
this?
Yet.
Okay, but have people written them before? Like Alexei Radul maybe, or Jerry Sussman?
It's one of the assignments in the, it's one of the exercises in the book. But,
the software designed for flexibility.
Yeah,
okay.
So I guess people have written it.
Okay.
But it's not in the book itself, yeah.
Okay.
Yeah.
You should be able to write an interpreter for a scheme like that, I think. Okay, cool.
Yeah.
All right, thank you.
Thanks. That was a really interesting presentation. I noticed I'm coming from physics, so propagator means something a little different in quantum field theory. And but I was struck by your example that you had a more complex example propagator network, and I think I noticed it has a cycle in it, right? And so I'm wondering, could you comment on that? Does that make it? Does that pose a challenge to implementing and computing to filling in all the output values in a distributed setting?
Yeah, it is possible that you could have something that is not computable from all the inputs, and but there is actually no cycle in the example that I gave.
I might have missed it.
Yeah, the arrow is probably too small. So in a well-specified propagator network, the order of execution should not matter. It should not matter whether you executed one propagator first or later, or where it was executed. The time of the execution should not matter at all. So there could be networks which don't converge to something to an actual value, and I don't know if how it can be eliminated. I haven't really looked at that, but yeah, that is something that has been bothering me as well. Yeah, but we also merge partial information together. So since we don't overwrite anything into a cell, that eliminates a great deal of problems like race conditions and things. So if when we merge things, the value of a cell doesn't change. That doesn't trigger the propagators that come after that. So that does eliminate a large class of problems, but I can't be really sure if it eliminates all problems. I'm not sure about that. Yeah.
Thank you.
For me, it was the merging thing that's the most confusing, because so you showed the example of the 1 to 5 with 2 missing in one and 4 missing in the other, and you end up with 1 to 5 with all 4 of them. What happens if the value of the third entity is different between the two? How do you resolve if there's actually a conflict in the output from the two?
Yeah. So if there is a contradiction, you do raise it, and maybe in the case of degeneracy, that could be a bug in your code. If you have 2 different paths which are producing different results, then something is wrong somewhere. And maybe you can handle the conflict by prioritizing one implementation over the other. Maybe you just use the older code instead of the newer code. So when you have the unmergeable things, the fact that you raise the contradiction is actually a feature. So if your propagators are producing unmergeable things, then there's something wrong with the design of the network, right? So you should be avoiding that. Yeah.
Thanks, Arun. That was great. How would this compare to unit testing? Is this a form of automated unit testing, or does it away with unit testing? How do you view that?
So the unit testing is usually done at build time, and we don't. Once the program is built, you don't really think about correctness anymore. But these are things that happen in runtime. So you are actually running multiple implementations of the same function in runtime. That does incur a performance cost, but it's probably okay for many things. Yeah.